Well, good morning. How are y'all doing today? A quiet morning, I think. You all know we're having a test in 1 week, so a week from today. Toward the end of class today, we'll have a quiz on the unit circle, so as we talked about before. And that'll be, though, the last little bit of class. It shouldn't take us too long, but the last little bit. Any questions about what's going on with that stuff? Go ahead.
How many units does the test cover?
The test is covering Chapter 6. What we've covered in Chapter 6, yes. Okay, so that's what the test will be covering. Sections, what was it? We've done material sections 6.1 through, we will be doing 6.6 there, so 6.1 to 6.6. What we've covered, you know, if we didn't cover it in the section, then you're not responsible for that, but so it's our first test, and that'll be next Tuesday, which is September 23rd. Oops, sorry, I was writing without switching. Thank you. All right, next Tuesday, September 23rd, 6.1 to 6.6 are the sections on there. Today we're having a quiz on the unit circle. You will see that unit circle again on the test next week, okay? You will see information about the unit circle. Remember, on the test, we're not using calculators. Not on this one anyway, okay? Okay, so let's get started then with going back for a minute to what we were covering last week. At the end of last week, somebody tell me what we were covering at the end of last week. What do you remember from Thursday? I always like to see what we remember from Thursday to Tuesday. What's that? Graphs. We were doing graphs. Graphs of what? Okay, cosine wave. What else? Sine wave. Anything else? We started, okay, what else did we look at? The cosecant and the secant. Did we get to the tangent and cotangent? No, that's where we cut off, right? Okay, because those were a little different. The secant and cosecant were based off those sine and cosine graphs. So to start out, I'm going to put these back up here just for a moment to kind of just remember where we were. Remember what the graphs looked like, okay? We want to be familiar with what those things look like and some of the properties of them. So y equals sine x. What do you know about y equals sine x, the graph of that?
It's the amplitude of it is y, or, well, the amplitude will be 1.
The amplitude's 1.
And the period would be 1 as well.
Period is?
1x.
No, not quite. Amplitude's 1. Period is 2 pi. Okay, the period's 2 pi. Why? Well, for one thing, when we're drawing that curve, it goes out 2 pi units. Every 2 pi units, it repeats itself. That's probably the easiest way to look at the period of a graph. Okay, every 2 pi units, it repeats. So when I place 2 pi units here marked off on my scale, on my x-axis, and then up to 1, the sine graph, if I want to put that on here, where do I kind of start my part that I'm working with at least? Okay, so I'm starting here at the origin. We know it doesn't really start there. It's just to help us draw it. Because really it goes on in both directions. Supposedly in the same pattern. It looks a little odd when I draw it. It doesn't look, you know, very correct like it should. But you all get the basic idea of what that looks like. If you're starting at the origin, coming up, you're going down, cutting down through a pi, coming back up through 2 pi. Every one of those integral multiples of pi is where we're having our x-intercepts. Okay? Every time we have an x-intercept there, we're on, you know, like 0 pi, 1 pi, 2 pi, 3 pi, and so on. That's where we're crossing through the x-axis. We said for the sine graph, the domain is all real numbers, and the range is from -1 to 1. Okay, remember the domain refers to your x-coordinates, and the range refers to your y's. And one other thing, do you remember if the sine function is even or odd?
It's odd.
It's odd, okay? It's an odd function. What do we know about odd functions?
They are mirrored across the y-axis and the x-axis.
Okay, so we've got they're symmetric about the origin then. And if we think of how we would fold that, we would fold across y and across x if you're visualizing that. So it's an odd function. We also know that that means that the sine of a negative angle is equal to the negative sine of the angle, of the positive angle, okay? So that was part of our odd properties as well, was how to convert if we had a trig function of a negative angle there, how we could make it turn into the positive angle, so to speak. All right, which functions graphed off the sine function? The cosecant. We use the sine to graph the cosecant. To save a little confusion, though, I'll go over here and redraw the sine, just a sketch of it. And so we had, our sine graph was looking like this. I'm just kind of putting it in there because right now we're trying to see y equals cosecant x. The cosecant graph, we said, will come off of the crest of the sine and look like these parabolas. It has asymptotes in between. Everywhere the sine graph had an x-intercept, the cosecant graph will have a vertical asymptote. The actual graph we're looking at here is all these opening upward, opening downward parabola shapes with the asymptotes in between those. Okay, that's what we're actually looking at for the graph of the cosecant. What we want to remember about that is where the cosecant's undefined. Okay, the cosecant's going to be undefined when the sine is equal to 0, because cosecant is the reciprocal of that sine. So if the sine function is equal to 0, then the cosecant will be undefined and have vertical asymptotes on its graph at those places. We might want to kind of put out here, even though we haven't seen the tangent and cotangent graphs yet, we might want to put out here just that the one of those two graphs has the same places where it's undefined, the same vertical asymptotes. Which one would have the same vertical asymptotes as this graph? Would it be the cotangent graph or the tangent graph? The cotangent, because the cotangent is the cosine divided by the sine, right? So cosine divided by sine, so if sine's in the denominator, again, it's going to be undefined wherever the sine is equal to 0. So we'll keep that in mind, and here in a few minutes we'll look at that graph. What about this one? What's the domain? Well, we've got to say x can't equal those integral multiples of pi, because it's undefined there. And the range, though, will be from where to where? Negative infinity up to -1, and then we'll unite that, or do the union of these two intervals from 1 to infinity. Is this function even or odd? Which one? Odd, right. It's odd also. It makes sense. If the sine function's odd and this is the reciprocal function, it's going to be odd also. Period is still what? Yep, 2 pi. We have one opening up, one opening down, then we repeat every 2 pi units. What about amplitude? Yeah, we don't really look at amplitude in the same way for a cosecant graph, but what we do remember, in order to get the cosecant graph, we look at the amplitude off the sine function that would go with it. Okay, so when you're graphing a cosecant, the best thing to do is mark out where it says cosecant and put sine and graph that based off your amplitude and period. and then put in these U-shapes everywhere, okay? And the U-shaped part is your cosecant graph. So if you're sketching that by hand, that's what you would look at. Okay. Now we also looked at the cosine and how the secant graph related to it in the same way as what we're seeing here. So those work very similarly. Let's put the cosine graph up here. Y equals cosine x. The sine and cosine graphs are the ones you'll see the most by far in here. But we do want to be familiar with the others as well. Cosine graph, where do I kind of start it? What does it go through on the y-axis? Yeah, up at 1. So we've got something like this going on now. It's the same shape as the sine graph, but it's just kind of shifted over. It's been shifted over pi halves units. So it's going to be that same overall shape. To get the secant, we would do the same as we did with the sine for the cosecant. We would put the U shapes off of the curves here. Okay, so we'll leave that part as it is. The amplitude here is still 1. Period is still 2 pi. The domain is still all real numbers. And the range is still from -1 to 1. Okay, so it's very much like the sine function. Sine and cosine we're doing, just a little bit more work with. We talked about their equations as well, and the form of them being y equals a sine omega x, y equals a cosine omega x, right? You remember those? When we tried to find the equations, we'll look at that a little bit more too before we're finished. Any questions about the cosine or sine or cosecant graph so far? We want to recognize, we want to have a general idea of what they look like, what they go through, their shape, some general things about those. Do we need to put secant up off the cosine? Well, we'll put it just to follow. You all are looking a little unsure, so let's put it just to follow. We've had a weekend since then. Now where we had x-intercepts of the cosine graph, that's where our secant graph will be undefined because of it being the reciprocal function. We flipped it over. So the x-intercepts for the cosine were at which values? Where did we have our x-intercepts for the cosine?
So pi halves and 3 pi halves.
Right, pi halves, 3 pi halves. It was at those odd multiples of pi halves, right? So here we know that this function is going to be undefined at those values. X cannot equal odd multiples of pi halves for this graph. That is where our asymptotes will be placed. Whoops. And then we remember what our cosine graph looked like, and off the curves of the cosine graph, that's where we're going to hook up those secant parts. So it's going to look like this. I'm going to draw it this time without putting the cosine graph in here, so you can see more exactly maybe what it would look like. Well, like I say, I'm not an artist up here. Y'all have to bear with me a little bit and go by my sketches. It's pretty close though, okay, to what it would look like. This is what your secant graph would look like. It's based off of these shapes are based off the curves of the original cosine graph, if you think about where the cosine graph would be there. Any questions there? Range is still going to be the same as it was for the cosecant. Okay. We forgot to say that cosine's even, so is secant. I'll go back over here and put cosine is even. Okay. We have, that means it's symmetric about the y-axis. If we fold over the y-axis now, we see that the two parts match up perfectly. So what about the tangent and the cotangent? Let's look at those for a moment and their shapes. Y equals tangent x. We want to note that the tangent function is equal to the sine over the cosine. And we remember that identity from one of the other sections here in the textbook. So we also know that tangent is going to be not cosine undefined, but tangent of x is undefined when the cosine is equal to 0. The cosine was equal to 0 at those odd multiples of pi halves. Okay, so let's put my general graph back up here. All right, so at odd multiples of pi halves, this tangent is going to be undefined at those odd multiples of pi halves. So we're going to put in some vertical asymptotes. We notice so far the only connected or continuous graphs we have are the sine and cosine graphs, where they just, continuously, we can leave our pencil down and draw sine and cosine waves all day. If we want to draw secant or cosecant graphs, we would have to lift our pencil up every time we make one of those shapes. So they're discontinuous. This one's also going to be discontinuous because we've got these asymptotes in between places here. Now, might be a little tougher for you to plot points. You could plot points, but since we're not using a calculator, that may make it a little tougher. But we can guesstimate a little and get some of these values just to let you see where this stuff's coming from. Overall, though, I want you just to recognize these graphs, be able to duplicate a general sketch of what it would look like. We know that if we put in 0, I'll do a little chart over here just for the heck of it here, but if I put in 0, what is the tangent at 0? Be careful. The tangent at 0 is actually 0. All right, so let's think. Let me go over here to the unit circle just a moment. Okay, here's 0 degrees, which is 0 radians also. The coordinates here are, what are the coordinates? 1, 0. We know the tangent at 0 will be the y over the x. So the tangent at 0 is 0 over 1, which is 0. Okay, remember 0 in the numerator, 0, 0 in the denominator is undefined. Okay, so that's how we're getting this here. If I put in x, I get 0 out for y. So that would give me this point right here. Now, if I'm choosing points, this is where it may get a little tougher for you to get these. I don't know, but between 0 and pi halves, what might I choose?
Pi fourths.
Pi fourths is a good candidate there. So let's put in pi fourths for x. The tangent of pi fourths is? It's 1 because it is the square root of 2 over 2, the square root of 2 over 2, right? Square root of 2 over 2 over the square root of 2 over 2. The tangent at pi fourths, I'm going back to my unit circle a minute. It's my x-axis, that's my y. Here's my pi over 4 angle. My coordinates here, square root of 2 over 2, square root of 2 over 2. Making the tangent of pi fourths be the y over x. They're the same though, right? So we get 1 for the tangent. What if I went to negative pi fourths? What's my tangent there going to be?
Should also be 1.
Yeah, wait. Tangent at negative pi fourths will be what? Negative 1. Because we still have the same coordinate values, we're going to get that 1, but one's negative and one's positive, so it's going to be negative 1. Let's go back over to my tangent graph here. If I put pi over 4 in for x, then I got out 1. If I put in negative pi fourths, we saw we got out negative 1. All right, what do we have there? Pi fourths, we need some coordinates. Pi fourths 1, negative pi fourths, negative 1. Okay, it's looking kind of odd. All right, if you put in anything else there, though, you're going to get some things you're going to have to work a little more with those radicals. You know, if you put in your pi thirds, pi sixths, you can do that and get some decimal approximations with your calculator and see where they are. But I'm going to go ahead and show you what this graph looks like. Overall, the tangent graph, or one period of the tangent graph, resembles y equals x cubed. It's not the same, but it resembles y equals x cubed. It does something like this. Now remember, these are curving and they're getting close to the vertical asymptotes, but they'll never cross over those vertical asymptotes because the graph is undefined at those places. So it's boundaries for us. So we have this shape here, and then it just repeats. So it's going to go through pi like that. Whoops, it's supposed to be going through 2 pi. Okay, and it just keeps on doing this. Whoops, I got hold of that. So it keeps on doing this same shape over and over repetitively. What's the period of this function? How far does it go before it repeats?
It's 1 pi.
This one's 1 pi, right? Does everybody see that? Look at the graph there. It goes out 1 pi. We're going from negative pi halves to positive pi halves. If you want to think about it right up here, you put the cursor on it here. Well, maybe. Wrong thing. All right. So if we go down here, we see first off it's an increasing graph. From left to right, it's going up. So as we read the graph from left to right, it's going in an upward motion. So it's increasing. It's going this way. If we look at just one little section, I guess we could say between 2 vertical asymptotes, because that's what's being repeated over and over, we see that this repetition is occurring from negative pi halves to positive pi halves, or that would be 1 pi unit, or from pi halves to 3 halves pi. Any way you look at it, the period of the graph here is pi. All the other graphs so far have been 2 pi periodic. Tangent and cotangent are both pi periodic, though. Again, we don't look at amplitude here. What does happen, though, if we have a graph, maybe instead of just y equals tangent x, maybe we have y equals 4 tangent x? What's that going to do to our graph? What did it do to your graph when you had y equals x squared compared to y equals 4x squared? Does anybody remember? It does what?
It makes your the y value the highest y value possible for the not the tangent, cotangent will make the highest y value possible. The one like the 4. So like if you had 4 sine x,
If I have 4 sine x, what's that going to do? Here,
your
puncher.
highest y or lowest y will be either 4 or negative 4.
Okay, so what he said was that if we had 4 sine x, the highest y and negative y, or highest y and negative y, highest y and lowest y would be 4 and negative 4. That's what you were saying. And that had to do with the amplitude. We don't really deal with it that way, though, here. So what happens if we have the 4 tangent x? It is going to do something, but what?
Would that be where your 45-degree angle?
Would the thing be? It's going to stretch it up more quickly, is what it's going to do. It's going to increase more rapidly, because if I've originally had y equals tangent x, and now I'm going to multiply that tangent x by 4, then the same values I was putting in before, they're going to increase or get larger more quickly. So for the graph, it kind of stretches it upward. Okay, it makes it more narrow, more thin, because it's increasing more rapidly. If you recall from your algebraic functions, when we had y equals x squared, we said that looks something like this, right? There's our parabola for that. And then we had y equals 4x squared. It's going to make it more narrow. Okay, I'm exaggerating here on this, and it's not symmetric, unfortunately, but here's what happened. When I put in 0, I still got out 0 there, but if I put in 1, I get out 1, 2 is 4, 3 is 9. Down here, let's put in those same values. 0, it's still going to be 0. Put in 1, now it's going to be 4. So instead of being at 1, 1, all of a sudden I'm already up at 1, 4. Okay. And then 2, when I put in 2, I get what for that? 16. Actually, it increases even more rapidly. We're up at 16. I put in 3. 36, right? Okay. So see how it's growing more rapidly? Those points would be getting up higher more quickly. And so it's going to make that shape more narrow, kind of stretch it upward more so. The same thing's going to happen on your tangent. It's going to make it increase more rapidly there if you have that multiplier out in front. So just to kind of have an idea, you want to know that basic shape, but that's what happens with those numbers out front there. All right, so that's our tangent graph. Our basic tangent graph, we said, looks kind of like y equals x cubed. One period of it does, at least. That's how you might think of it to make sure you get it drawn in there right. It goes through the origin in that same direction as y equals x cubed. What's the domain here for the tangent graph? It's not everything because we got asymptotes. X can't be those odd multiples of pi halves. That means x can be anything but those. What's the range here? It is all real, negative infinity to positive infinity. We're spanning all of that y-axis when we look up and down there, the way they're continuing upwards, continuing downwards. Even or odd? Odd. Good. Okay. Well, we know the cotangent is the reciprocal of the tangent. So what does that tell us about overall just the graph in general? One thing it tells us is where it's going to be undefined. Where the tangent has x-intercepts and is equal to 0, what's going to happen with the cotangent? Where the tangent's equal to 0 at those x-intercepts, here at the origin, at pi, at 2 pi, where it's equal to 0, if the cotangent's the reciprocal, then what's up with the cotangent at those places? It's going to be undefined at the places where we had the x-intercepts here. And where we had the undefined parts here, that's where the cotangent will equal 0. So it is going to look a little different from this one. Let's see. Y equals cotangent x. We know that's 1 over tangent x, or we could think of it, as we mentioned earlier, cosine x over sine x. And where the sine or the tangent is equal to 0, the cotangent will be undefined. We're getting lots of practice drawing graphs here, drawing coordinate systems. All right, so the tangent went through the origin. At the origin, the cotangent is undefined. At pi, the cotangent is undefined. Undefined at 2 pi, because the tangent was 0 at all those places. Again, you could plot some points here. Here's what's going to happen here. We already said, these places where the tangent was undefined, the cotangent is going to equal 0, so we know it's going to cross through these points here. But it actually kind of reflects over, if you want to call it that. It looks like this. Okay, so it continues on in this manner. Still, the period of the graph is pi. The domain will be x cannot equal integral multiples of pi. The range is still all real numbers. It's an odd function. Notice, remember the tangent, how it went up like the y equals x cubed shape, and it was increasing. What about this one? Is it increasing or decreasing? It's decreasing. If we read it from left to right, we're starting up high, coming down low, so we're decreasing here. Is it continuous or discontinuous? When I draw this graph, do I have to raise my pencil up to draw it? I do, because why? All those vertical asymptotes. So it's discontinuous. It's only continuous if I can just keep drawing without moving my pencil. Okay, that's kind of an easy definition, but that's something for you to think about. If you're going on into calculus, you'll hear more about that then. I'm just trying to give you a little, every now and then I'm trying to put a little something in that you'll hear again if you're going into those calculus classes, okay? And you'll hear about continuous in there. You'll hear about increasing and decreasing in that class, okay? So, but we can recognize those things with these graphs as well, and hopefully they'll help us, remember some things about the graphs themselves. All right, did you have questions from your assignment that you were practicing on today, for today? I think you all were working on page 404, is that right? I believe. And you'd started looking at the, wait a minute. Okay. Started looking at some of the graphing problems as well, maybe? On 403. Well, 403 was, never mind. I've got them backwards, I think.
Yeah, I got a 404, 11 through 29.
Yeah, that's, okay.
413.
413, we did have a few, right? Numbers 3 through 12.
So we got 4, 5, and then 9 through 14, 25, 27.
Okay. All right. Anybody have a question about the assignment from last Thursday or the practice problems dealing with the graphs? Yes, go ahead.
Can you go over 39?
And what page are we on, please?
That was
Well, what is
404.
it? Okay, I was going to say, what does it say? And I can probably find it. So, okay. All right, 39 on 404. Let's go over there. Y equals cosine 4x. Here's what we want to know with this stuff, okay? I know it said just to graph it and so forth. When you're graphing these, you will need to recognize what the amplitude and the period is in order to effectively draw the graph. So the first thing I'm going to put up here is the amplitude. What is the amplitude here? Amplitude is 1. Remember your general form, or if you weren't with us last class and haven't yet watched the class, remember if you're out, you can watch the class, right? With your popcorn and all. So I want my son to watch the class because he just missed 2 days of his pre-calculus class. He's in a different class, okay? So he missed 2 days, and I said, you need to watch my class. And he doesn't want to. I'm insulted. All right, y equals a cosine omega x, remember, was our general form. A, actually the absolute value of a, is the amplitude. And the period is, what was the formula for that period? 2 pi over omega. Let me put in here also, though, if you're working with a tangent or a cotangent, since their period was pi on the general graph, then to get the period of any tangent or cotangent graph, you will just use pi over omega on a tangent or cotangent. It's based off what the period is from the function. So pi over omega if you're doing cotangent or tangent, everything else, 2 pi over omega. All right, so what's the period for this graph here? Yeah, 2 pi over 4, which is pi halves. 4 is the omega value. Okay. We want to graph this and see what it overall looks like. Tell you what, let's go back up here. Since it said the period's pi halves, we know we're going to go out pi halves units before we repeat. And just to make it easier to see on the graph, I'll label pi halves here. What's halfway there? We always want to label what's halfway through the period of the graph. Pi fourths would be halfway. Okay, the amplitude is still 1, so we know we're going up to 1, down to -1. This is a cosine graph. So this one's going to look something like, since it's cosine, I can't draw though. My pen got stuck here. Well, something like that.
So would that be continuous?
Yes, cosine is continuous. Cosine and sine both are, but the others aren't. Because this one's defined everywhere. Now, so that omega value changing, instead of just saying cosine x, where it said cosine 4x, when the omega value changed, that changed the length of that period of the graph, how far we went before we repeated. Now, actually, I went ahead and drew mine out, here's pi halves. But if I'd kept it on that same scale as before and the period was pi halves, it's going to make it a lot more condensed into that 0 to pi halves part, isn't it? So it's actually making it a little, we're getting more waves in before 2 pi than what we did before. Does that make sense? Before we just drew it out, and there was one period of the graph. Now we're getting a little bit more in there before we get to that 2 pi value. Period of the graph here we said was pi halves, so to look at one period of the graph, we were just going initially from there to there, and then it repeats. The domain here is still -infinity to +infinity, and the range is still -1 to 1. Does that answer the question on that problem? Okay. So it's when the number's out in front of the whole function that it, makes it, on the sine or cosine, makes the amplitude higher or larger, or it stretches out the other functions. What else from this page? 403, 404, in that area. Go ahead.
Could you do number 47?
Okay, 47. So everyone finished with 39 here. (47). That's a good one to look at here. Y equals 2 sine x plus 3. Y equals 2 sine x plus 3. We've been seeing y equals a sine omega x. So what does this plus 3 do? It shifts it how? Up 3 units. That's a vertical shift there. Shifts it up 3 units. The whole graph, from whatever we would have had for 2 sine x, y equals 2 sine x, we're going to raise the whole graph up 3 units there. Anytime you add or subtract something to your function, it will shift the graph vertically. If you're adding, it goes up. If you're subtracting, it goes down. So here's what we'll have. Well, we need to know, what's the amplitude? Period? Yeah. 2 pi, because it's 2 pi over 1. The omega value is 1 here. 2 pi is what we get. Amplitude is up to 2. Whoops, I want to be careful drawing this one. Hold on. I have to leave myself a little space here. Still probably didn't leave enough. We know the period's 2 pi. So looking at one period of the graph here, first think about it, or this is how I'm going to advise you to graph it. First think about it without that plus 3. Forget about plus 3 for a minute. Okay, just graph what we just talked about. The amplitude's 2, period's 2 pi. It's a sine graph, so it's basically starting here at the origin. Looking something like this. I'm just dashing it in because this is not our actual graph. We didn't do the plus 3 yet. When I do the plus 3, I've got to shift this thing up 3 units. So instead of starting there at 0, 0, I would be starting where?
0.
At 0, 3. And how far up will it go to? Yeah, to 5. Down to 1. It's going to do like this then. Okay. Going up to 5, down to the 1. It's like we took that whole x-axis and slid it up there and put it across. Does that make sense? If you can visualize that, sometimes it helps to kind of think about how you can see it in your mind. Okay, we're taking that whole x-axis, we're sliding it up 3 units and leaving it there now. We just don't see the x-axis up there. But that's where the so-called middle of the graph would be. So our actual graph here is the one in black for the whole thing. Anytime you have something on the end, you're going to move up or down. Added or subtracted on that function. So that's a very good one to look at. So what is the domain now?
All real numbers.
Still all real numbers. What is the range?
1 to 5.
Okay, this time we've changed it to 1 to 5. The y's are only going to be in that part from 1 to 5. I don't know what that was. All right. So there's a few others here where something's added or subtracted onto here. And there were some where you had to find the equation of the graph. We looked at that last time, didn't we? Finding the equation, writing the equation. We didn't do the equations? I thought we'd done those. Let's do one. All right, let's go over. I thought we looked at one where we had the graph and we figured out what the period of the graph was. Did we not do that in here? Yeah, I see some yeses. Okay. Yes, go ahead.
I just have one question on the last problem. When you went up 3, why did you go up to 5 doing that? From 3 to 5.
Okay, because my amplitude was still 2.
Okay.
So if I'm starting the graph here, okay, I moved the point that was here at the origin. You see where I'm pointing up there? Up 3 units, so it's there starting. But I still have to make, it's like, I'm going to put something else in here on the graph. It's like now my x-axis came up to here. I don't leave that part, but that's where my x-axis was, and I came up, and the crest still has to go up 2 above that and down 2 below that.
Okay.
So that's why it's going up to 5 and down to 1 there.
Okay.
Yeah, no problem. Anything else on that one? That is a little harder to look at when you're sketching. And to make it a little tougher, we'll put in some horizontal shifts also. This was a vertical shift. We won't do it just yet. All right, does somebody have one? Let's see. Y'all were working through 71, so I'd assigned these, I see, but let's just pick one here. How about 65? Did y'all do 65? Anybody? Okay, didn't get that far. All right. Then I guess it's a good thing we're doing it. Actually, they didn't label pi and they didn't label 3 pi in the book, but you can see what those are by the way the graph's laid out. Bad drawing today. All right, let me find where I am here. So this looks kind of bad. So we want to write an equation for this graph. That's what our goal is, write an equation for this sketch that I've made up here. So it look like a sine or cosine graph to you? Cosine. So we're going with this form here. Y equals a cosine omega x. So what is the amplitude? The amplitude appears to be 3. What's a going to be, though? -3. Why is a -3?
Because
It's been reflected over that x-axis. You see, we're not starting up on the y-axis. We're starting down on the y-axis. Do you see that? We're starting down there at -3. As far as we were talking about starting or where it crosses through the y-axis is what we're referring to there. So our amplitude is actually going to be, our amplitude is actually 3. The a value itself that was -3. the absolute value of that gave us the amplitude. Period here, by looking at the graph, can we tell? Wow, I hope I drew it correctly. Let's see. What does the period of this graph look to be?
4 pi.
4 pi. Well, good. I drew it well enough to where you could tell that then, at least. We went 4 pi units before we repeated. So if I'm thinking about, again, starting here at this y-axis value, I go up, I come back down, I'm here, then it would repeat. Do you see that? Period's 4 pi. Right now, I'm going to move over here to the left side. My equation would say y equals -3 cosine omega x. The period is not the value for omega. I can't just stick that 4 pi in there for omega. So what I have to do is figure out what that would be. I know that the period of this graph is 4 pi, but I also know that in general, the period of a graph is equal to 2 pi over omega. I can use those two bits of information together to figure out what omega would equal by setting 2 pi over omega equal to what we know the period to be, 4 pi. Now we can use our algebra and solve for omega. How are we going to do that?
You multiply 4 pi over 1 by omega over 2 pi.
Let's just, okay, I see what you're doing. You're clearing it all out at once. I'm going to take just this step here, multiply by omega. 2 pi equals 4 pi omega. And then, though, what would I do? Divide by the 4 pi. Okay, I'll just do that. How's that? So we get, what's going to be omega? What's 2 pi over 4 pi? 1/2. So 1/2 is what omega is. See, those pi's cancel and 2 goes into 4 2 times, but I'd have 1 on top, so 1/2. So what's my equation? Y equals, remember I was trying to get an equation here. Y equals what? All right. -3 cosine 1/2 x. -3 cosine 1/2 x. We were finding that value to put in front of the x there in the argument of the trig function. Questions there? Go ahead. Yes.
So is it always going to be 2 pi over omega when you're trying to find the period? Is that going to be for every graph?
When I'm trying to find the period of what?
Well, you said that 2 pi over omega equals the period. So is that going to be correct for every graph when you're trying to do that?
Not for every graph, but for which ones? Sine and cosine, secant and cosecant. Okay? The only ones that is not true for is if we're dealing with a tangent or cotangent, then we would have to use pi over omega. Okay? For a tangent or cotangent, use pi over omega. But for all the rest, and we actually are working with cosines and sines. I think we're only working with cosines and sines. Well, we are only working with cosines and sines where we're writing the equations. So that's going to be the part you're focusing on there, and you would be using 2 pi over omega. Do y'all remember, did we do one of these Thursday at all? It came back. Some of you it came back. Some of you said no. All right. I believe we did one Thursday. All right. Any other questions from what we were looking at so far? Just to get you thinking here about the horizontal shifts, the phase shifts, I'm going to just show you a little bit about that. This is just the very start of 6-6. We'll finish this up, though, on Thursday. And we'll talk about the whole chapter some more on Thursday and do some reviewing and so forth. Phase shift is a horizontal shift. We looked at a vertical shift just a while ago. You might remember from a previous algebra 2, I don't know which class it would be in, some class, right? You might remember some of those basic functions and how they worked. And I'm going to go back to one we used earlier today, y equals x squared, and compare that to y equals x squared plus 3 and y equals x plus 3 squared. Okay, we want to see what the differences in these are. These are the types of graphs where y equals x squared is a common graph. So since we know what it looks like, we should be able to have some idea of what these other two graphs look like without plotting points and all that. What does y equals x squared look like? It's just a parabola with the vertex at 0, 0. Just our most basic parabola, I guess we could say. Y equals x squared plus 3. What happens with it? What does that plus 3 do? Up 3. So now the vertex will be, up here at 0, 3. Same parabola, moved up to 0, 3 for the vertex. Okay. So this is what we've seen so far. We have a function, we add something to it, then we shift the function up. We shift the graph up that many units. This one over here, let's put it in black. Now what's it going to do? What's this plus 3 there doing?
It shifts it on like the x-axis 3 units.
Okay, it shifts it on the x-axis 3 units. Which way? We want to think to the right. Okay, but let me ask you this. If it shifted to the right, then you would have your vertex at 3, 0, wouldn't you? Meaning that 3, 0 would work in that equation. If I'm saying 3, 0 works in that equation, I'm saying when I put 3 in for x, I'm getting out 0. Is that true? You see that's not true, don't you? 3 plus 3 is 6. 6 squared is 36. So I would not be getting out a 0. It actually shifts it to the left 3 units in this case. Horizontal shifts make you have to think opposite, I guess. Okay, with vertical shifts, it's exactly what you would think. If it's plus, it's up. If it's minus, it's down. But horizontal shifts, if it's plus, it's going to be left. If it's minus, it's right. It's opposite what you would think on the horizontal. So this will be left 3 units. Now, does that point work for the vertex if I'm at negative 3, 0? Do you see that? If I plug in negative 3, I do get 0 out, don't I? As far as just kind of verifying where you are here. So that would be a shift to the left. The horizontal shifts is what we call phase shifts when we work with the trig functions here. We're going to look at the phase shifts. They're usually noted. Notice that the plus 3 was inside those parentheses. And that's how we recognize those horizontal shifts. They are written within the function. So that is within the part that's getting squared. The x squared being the original function here. If we put something in with it that's also getting squared, then we're doing a horizontal shift. If we just tack something on the end of the function, like with the x squared plus 3, then we're moving vertically. Okay. So with the trig functions, what happens is we have that argument of the trig function, which is generally in parentheses, not always, but generally. But if we have y equals sine x, and then we have y equals sine of x plus pi, that would be a horizontal shift because it's written within the function. It's still part of what we're taking the sine of. This would be left pi units. If I have y equals sine x plus 2, like that, this is up 2 units. I want you to see the difference in how they're written. Okay, see the difference there? To note phase shift in general, we're going to add something else to our formula for the function. Y equals a sine, we're going to put something else in here, omega x minus phi. That's what your book uses, okay? So we got a little more Greek here, omega x minus phi now. And the phase shift, when the function is in this form, the phase shift will equal phi over omega. This one up here that I'd written, sine of x plus pi, it's not really written in that exact form because it doesn't say minus something. Do you see that? So if I think of this one in that form, I have to say y equals sine x minus pi to get it to look like the form I gave you with the minus in it, so that phi is just this part here. Phase shift becomes negative phi, or negative pi, too many Greek words here, negative pi over 1. This 1 right here is omega, which is negative pi. And because it's negative pi, that tells us that we would be moving left pi units. You all could tell that by looking at the function with it in the parentheses because of what I just told you about the x squared business, I think. I'm guessing. Maybe. All right. We'll start class next time talking a little bit more about this. If you want to try to look ahead with it, in 6.6, here's what we will be doing, but you may not get this part just yet, okay? You might need to wait till we come back to class Thursday on this. But on 6.6 on page 424, eventually we'll be finding, the amplitude, the period, and the phase shift for these. You can try those, but I don't know that you'll, well, you can at least find the amplitude and period. You might get that phase shift also. Work with it a little bit. 6.5. What were we adding to 6.5? 6.5 you already had. That's where you had 4, 5, 9 to 14, right? That stuff.
Yeah, 4, 5, 9, 14, 25, 27.
So let's add in there 15 through 25 odd, and that was on page 413. So those you should be able to look at and do some sketches of graphs with tangent, cotangent, just to get the idea of what you're working with there. Tangent, cotangent, secant, and cosecants. Just adding in those tangents and cotangents. Any questions about that? We'll finish up the material on Thursday. Let's go ahead, if there's no questions, and do the unit circle quiz. I just want to make sure you have enough time. I don't want to give you too much time, but I don't want to give you too little time. Here's what I want you to do on it. It looks just like what you had on D2L. Okay, you've seen this, hopefully, before. You are going to label the coordinates, the x and y coordinates for me. Over here, there's little blanks for them. Okay, you're going to label the radian measure. It's got a little blank. And then there's a little blank with a degree symbol up in it, so that's for your degree measure. And go around the circle and label those. Please be sure and put your name on your paper, okay, so that you will get credit for it. Any questions at all? When you're finished, just turn it in and you're free to go, okay? I'll see you back on Thursday. Thank you all.
Sorry it took so long.
Oh, no problem.
Went back over and checked my work like 3 times.
Oh, that's okay. We're still at class.